On this video, I'm going to show you how to solve the ALEKS problem called Deducing a Rate Law from Initial Reaction Data. For this problem, you're going to be given a set of data for a chemical reaction. I'm going to number our data sets, number 1, number 2, and number 3. And we're being asked to come up with the rate law for the data and also the value of the rate constant, including units, which is definitely going to be tricky. When we're being asked to solve the rate law, that just simply means that we're being asked to determine the exponents in the rate law. So we know that the rate is going to be equal to K times the concentration of N2, because that's what we're working with here, to some exponent X. And we have to figure that exponent out. And also the concentration of H2, because that's our other reactant, to an exponent, we're just going to say Y. We've got to figure that out as well. So again, coming up with the rate law means that we need to come up with the value of X and Y. To do that, we're going to begin by selecting two sets of data from this data table. We want two sets of data. Let's just start with two sets of data where the concentration of N2 is exactly the same. So that means I'm looking at these two data sets right here where the concentration of N2 is not changing. I'm going to start with that. And what we're going to do is write a rate law in this format, filling in as much information as we can for data set number 1 and data set number 2. Again, I've chose those two because the concentration of N2 is unchanging. So we're going to use, for data set number 1, I'm just going to kind of rewrite this up here. We're using rate equals K N2 to the X, H2 to the Y. For data set number 1, the rate is 7 times 10 to the third. I'm actually just going to write 7 times 10 to the third, and I'm not going to worry about units yet, so I'm going to leave them off completely. And that is equal to the rate constant, which we don't know yet, times the concentration of N2 for data set number 1. N2 is 0.273, and that's going to get raised to the X, times the concentration of H2. For data set number 1, H2 is 0.832, and that's going to get raised to the Y. Now, underneath all of that, in the form of a fraction, we're going to do the same thing for data set number 2. Again, I picked data set number 1, N2, because the concentration of N2 is exactly the same. For data set number 2, the rate is 839. The rate constant K, we don't know. The concentration of N2 for data set number 2 is 0.273, that gets raised to the X. And for H2, data set number 2, concentration of H2, I'm saying 2 a lot, is 0.288 raised to the Y. So what we have here are two equations. I've got them kind of written in a fraction form. What I'm going to do to make this look a little bit more like a math problem is I'm just going to use one equal sign in between the two, and I'm going to begin by solving the left-hand side of this equation. 3 times 10 to the 7 times 10 to the 3 divided by 839. The left-hand side of this equation is 8.34. Now I'm going to work on the right-hand side of the equation. The rate constant K is the same for both reactions, so K divided by K is just going to cancel itself out. Also, the values of X and Y are the same, so 0.273 to the X is going to be the same thing as 0.273 to the X, so that's going to cancel out as well. And that's why we chose two sets of data where the concentration of N2 was exactly the same, so that it could cancel out. This leaves us on the right-hand side with 0.832 divided by 0.288, and those are raised to the Y. This, what I just did there, is a property of exponents. If you have a to the Y over b to the Y, you can rewrite that as a over b as a fraction raised to the Y. So I just took advantage of that. And then I'm going to solve the math that's inside that parentheses. So I'm going to have 8.34 on the left, 0.832 divided by 0.288. That's going to give me 2.89 to the Y. So I just solved inside the parentheses. The last thing that I need to do here is solve for Y. And the way that I'm going to do that is use log. You could also use natural log if you wanted. The log of 8.34 is Y times the log of 2.89. And I'll just solve for Y. The log of 8.34 is about 0.92, and I'm going to divide that by, this is a times, not a minus, that's a multiplication dot. The log of 2.89, and this gives me a Y value of 1.999. We're just going to call that 2. So we have solved one of the exponents here. we're going to repeat this whole entire process to solve for y. This time, since we've already finished working with the N2 data, this time we want to look for two sets of data where H2 is exactly the same. And that looks like we want to use data set number 1 and data set number 3. These data sets have the concentration of H2 exactly the same. So I'm going to use data set number 1 and I'm going to use data set number 3. For data set number 1, the rate is 7 times 10 to the third. The rate constant, K. Our concentration of N2 is 0.273, and we know now that that exponent is, oh, you know what I did? I made a mistake here. Y is 2, not X. Almost made a mistake there. Up here when we solved for y, even though we were kind of focused on N2, we solved for y, which is this term right there. Okay, 0.273 to the x times our concentration of H2. So we're on data set number 1, our concentration of H2, which is 0.832, and we know the value of y, it's a 2. Now we're going to do the same thing for data set number 3. For data set number 3, the rate is 1.7 times 10 to the 4. The value of the rate constant is K. Our N2 concentration is 0.664, and that's raised to the X. And our H2 concentration is 0.832, and we know that that's getting raised to the 2. And again, I'm going to fix my kind of weird looking equal sign so it looks like that. I'm going to solve the left-hand side, 7 times 10 to the 3 divided by 1.7 times 10 to the 4. The left-hand side, I have a 0.4118. For the right-hand side, I can cancel out the value of K again, and also I can cancel this term out as well. 0.832 raised to the 2 divided by 0.832 raised to the 2, they're just going to cancel. That's going to leave me with 0.273 divided by 0.664, both to the x. I am going to solve inside the parentheses next. 0.4118 is equal to 0.273 divided by 0.664. That is, 0.4111 to the x. I don't need to use the calculator for this. I can see that the value of x is 1. So we'll write that. We probably don't actually want to write a 1 over here. We probably just want to have no term at all. So there's our rate law. It's a lot of work. We've got that one part of the problem done. The last thing that we need to do here is solve for the value of K. To solve for the value of K, we're going to use our actual rate law that we discovered, and we're going to use any one of these sets of data. We can literally use any one that we want. I'm just going to use, data set number 1, just the one on top, and we're going to plug everything that we know into that rate law that we just discovered, this rate law right here. So we're going to say, I'm going to do this in a different color. The rate is 7.00 times 10 to the 3, and this time we do want to pay attention to our units, so I'm going to include the units. Molarity per second. And that is going to be equal to our rate constant, which we don't know, times the concentration of N2, which is 0.273 molar, and the concentration of H2, which is 0.832, also molar, and remember that that's getting squared because we determined that that was its exponent right there. So now what we need to do is solve for K. So I'm going to rearrange this equation in terms of K. And I'm going to get, if I take both of these, divide both sides of the equation by this, I'm going to get 7 times 10 to the third molarity per second. And I'm going to divide that by 0.273 molarity times 0.832 molarity, and that's going to get squared. Working out the number here is not going to be hard. Like the number part of this answer, 7 times 10 to the third divided by 0.273 divided by 0.832 squared. That much of it is not tricky. 3 significant figures, 3.70 times 10 to the fourth. The hard part is going to be figuring out the units in this problem, like paying attention to them so that we don't mess it up. We have a molarity divided by a molarity, so we can cancel that out, and that leaves us with 1 over second and 1 over molarity squared. So we would write that as molarity to the -2, and second to the -1. Or you could turn it the other way around, second to the -1, molarity to the -2.